Hi, and welcome to the Why Isn't My Brain Working Part 1 class. My name is Kinsey Self, and I will be your presenter this afternoon. I am the owner and founder of Progressive Health and Wellness. Progressive Health and Wellness provides completely virtual wellness consulting and education services. We combine a holistic approach with scientific and research-based analysis to accurately identify and effectively address the root cause of dysfunction and restore optimal function for the long term. Today, we're going to explore the intricacies and the complexities of the brain. I think it's a very underappreciated area of research and medicine and wellness. And in this class, in part 1, we're really going to we'll start off by diving into the breadth of the matter. So we'll briefly talk about statistics. Then we're going to jump into some brain anatomy and physiology. Don't worry, this class is designed for both the layperson and the healthcare professional, so I'm not going to get too complex. Then we'll get into the signs and symptoms of brain decline. I bet most of you will be pretty surprised at what some of those signs and symptoms are. To give you an idea, who here has ever walked into a room and forgot why? For example, or forgot where you left your keys. Simple little things that can actually be bigger signs of a bigger problem. This is the meat of the presentation, why the system breaks down. And this is really what delineates part 1 from part 2. In part 1, we talk about exactly that, why the mechanisms as to what causes degeneration in the first place. So we'll talk about the excitatory model of neurodegeneration, autophagy, the process of autophagy, and brain inflammation. In part 2, we talk about the underlying causes of those. So in other words, this section, the why the system breaks down, is the manifestation of what happens when the brain and the nervous system is under assault, essentially. What areas start to break down. In part 2, we'll dive into what's causing kind of the most common causes of the source of dysfunction. So like gut dysbiosis, for example, food sensitivities, hormone imbalance. We'll answer that aspect of it in part 2. And then, of course, we'll get into what can you actually do about it, right? Nutrition therapy and lifestyle for rehabilitating the brain and the nervous system. Okay, what spurred this fascination, and honestly, functional brain chemistry has become one of my biggest passions and areas of study. I went to a Mastering Brain Chemistry seminar. It was a weekend-long seminar a few years ago, actually. And they talked all about all of these different categories and the importance of brain health and what happens to the entire body when the brain and the nervous system starts to break down. And this was a slide that they provided where they talked about all of the different facets of brain health and brain chemistry. So we're looking at, stress, essential fatty acids. Methylation is a form of kind of activating the activation of B vitamins, and then methylation looks into specifically different processes involved with DNA synthesis, detoxification, immune regulation, things along those lines. Circulation and oxygen, contrary to popular belief, just because you're breathing doesn't mean that your brain is getting sufficient oxygen. Exercise, blood sugar regulation, environmental triggers and toxicity, gluten and food sensitivities, neuroinflammation. There's so many different categories to evaluate, right? But the thing is it's so critical because brain health and nervous system health impacts the entire body. And we'll dive into exactly what I mean by that and how. So let's briefly start off going over these statistics, the scope of the matter, so we can really understand and appreciate that, when we hear the term neurodegeneration, we're not just talking about the elderly, right? We're not just talking about Alzheimer's, which, by the way, also doesn't only impact the elderly. There is early onset stage Alzheimer's that affects people as young as 40 or 50 years old. To give you an idea, this issue is grossly accelerating. So Alzheimer's is the 6th leading cause of death in the United States. Combined, dementia and Alzheimer's kills more than breast and prostate cancer combined. One in three seniors, right? 1 in 3 seniors dies with Alzheimer's or another form of dementia. Now, interestingly, there's another global statistic that overlaps this, and that is the rate of obesity and overweight. So I said global statistic. That one specifically is actually more unique to the United States, but it's estimated about 69% at this point of the United States adult population. So, basically 1 in 3 is either overweight or obese. And diabetes and pre-diabetes statistics are starting to mirror this. Childhood diabetes is starting to affect 1 in 4 children. So the fact that they're causing Alzheimer's type 3 diabetes is not coincidental. And we'll understand that mechanism a little bit more by the end of this presentation. But when you also consider not just Alzheimer's, right, we have to look at dementia, which is technically different. There are certain signs, symptoms, and hallmarks, specifically biochemical and physiological hallmarks associated with autism. Dementia, though, is a little bit different. It's not limited to just the hallmarks of Alzheimer's. The worldwide prevalence of dementia is 24 million people. And the scary fact is that this figure is estimated to double within 20 years. We're already spending over $200 billion on Alzheimer's and dementia combined. Imagine what our healthcare expenditure is going to look like by the year 2040. In fact, dementia, type 2 diabetes, and obesity all together are expected to actually bankrupt Medicare within this time frame. Brain developmental disorders, so like I said, it's not just limited to the elderly. 1 in 8 children are diagnosed with a brain developmental disorder such as autism, ADD, and ADHD. At this point, 1 in 45 children are diagnosed with autism spectrum disorder each year. Back, about 10 years ago, it was 1 in 80 children were diagnosed. This is a rate of 119% increase just in the last 18 years. It is the fastest growing developmental disability to date. And that's coming straight from the CDC in 2014, right? We're 4 years later than that statistic now. There's autism awareness. I mean, we can all appreciate that this is vastly and hugely impacting our children. And then when you think about it, I don't mean to be doom and gloom or kind of depressing, but the children with autism are going to grow into adults. So think about how this is going to impact society in 20, 30 years. And this condition is not showing any signs, or I should say the spectrum is not showing any signs of slowing down, right? It begs the question, what has changed the most in the last, let's just call it 30 years? The environment. Our environment, from the food that we eat, the air we breathe, the water we drink, the vaccines we're exposed to. Over 80,000 different chemicals have been released into our environment in the last about 100 years. And a fraction of those have actually been tested for human safety, especially in the long term. So our environment is grossly different, even in the last 30 years, which is, we have to look at that when evaluating autism, Alzheimer's, any kind of neurodegeneration, any kind of health abnormality for that matter, but especially those impacting the nervous system. Depression is the leading cause of disability worldwide. Now that, when I first read that is an alarming statistic, that depression is the leading cause of disability worldwide. I almost wrote a book asserting that mental illness, at the root of mental illness, is brain inflammation. And the neuroinflammation model of depression is starting to gain a lot more area of research, a lot more attention, because there is such an association with it. So they're finding that when, in some cases, not all, but in some cases, when an anti-inflammatory is, like a steroid, for example, is co-prescribed with an antidepressant, people respond better. Depression is, very simply put, is not as simple as a neurotransmitter imbalance or a chemical imbalance. There's always a root, right? At the end of the day, you have to ask why until you can't ask why anymore. And we'll talk about, when we talk about neuroinflammation and how that affects the signaling and transmission of neurons, the expression of depression becomes pretty obvious. Okay, now that we can understand how this is affecting society, right? We all know of someone at this point that is suffering from some form of neurological condition or neurological issue, be it dysthenia, where they're just not as happy as they used to be, depression, autism, bipolar disorder, Alzheimer's, dementia, even just brain fog, right? Just the inability to think really clearly. So we all know it, and it's hugely impacting our society. So now let's get into understanding why. In my opinion, this is one of the foundational principles by which I operate. When you understand normal, identifying dysfunction becomes very easy. So what we're going to do is go through what normal looks like in regards to the nervous system and how neurons function, what a microglia cell is, and then we'll get into recognizing abnormalities and the causes of breakdown. So, brief review of anatomy and physiology of the nervous system. The majority of the nervous system is made up of two classes of cells, neurons and neuroglia. Neurons, despite accounting for only about 1/10 of the weight of the brain and the nervous system, neurons get all of the attention. So neurons are the ones that actually engage in cellular communication. They are the reasons that we can move our hands, that we can wave our arm, that we can even think or feel anything. We attribute that to neurons. However, neuroglia used to be, it got the name because from the Greek word of neuro, and then glia means glue. We used to just think that neuroglia was kind of this inert substance that just held neurons together. However, that is out the window, and we can now appreciate that the neuroglia is really accounts for the functioning and the preservation of neurons. So neurons, we'll start there because they're the most familiar. Neurons are highly specialized cells that communicate with the body by transmitting electrochemical impulses. Okay, so they will looking at the image here, in the top, this section right up in the sending neuron is where the electrochemical message originates. It then, the electrical signal, as seen by the yellow burst sign, travels to the nerve cell body, which then releases or stimulates the release of a chemical signal. Those are called, that's the actual neurotransmitter, those red dots right there. The neurotransmitters are like acetylcholine, serotonin, dopamine, norepinephrine, for example. Those are then released into the receiving neuron, the cell body of the receiving neuron. You can see here those little orange dots or red dots that are released into the orange docking stations in what we call a synaptic cleft. That then potentiates the signal down the receiving neuron, where it travels down the axon and then down to the dendrite, which is that kind of tree-looking thing at the very bottom. The dendrite then makes connections to the other neurons that it's connected to, and that is how the electrochemical message is transmitted from neuron to neuron to neuron. That is a very simplified example. One thing that I do want to point out here is the needs of the neuron. So in order for all of that to happen, there's several pieces to the puzzle that have to be in place. For one, in order for neurons to survive, they need sufficient oxygen. So as I said at the beginning of the presentation, just because you're breathing doesn't mean that you're getting sufficient oxygen, especially to the brain. We have to look at factors like, for example, anemia. So do you have enough red blood cells, and are they appropriately shaped to carry and transport oxygen from our lungs up to the brain and then delivers, directly to the neurons? Fuel and nutrients. glucose, fatty acids, and then nutrients like vitamins, minerals, different cofactors, and then stimulation. Name of the game with the nervous system, if you don't use it, you lose it. So stimulation, another word for it is activation. This kind of has two different categories. One, we're looking at actual usage of the brain. So exercise, for example, learning new skills, challenging yourself. You know, you might have heard that even if you just brush your teeth with the opposite hand, that's reprogramming and rewiring different aspects of the brain. Learning a new language, for example, playing brain games or just games in general. So using your brain. And then the other side of the coin is pretty much almost everything in the body is a two-way street. So the brain essentially sits up in this little black box called the skull and sends messages via the hormonal system and the nervous system to communicate with the rest of the body. Well, it also relies on communication from the body via neurons, nerve stimulation, and hormones to report back how it's doing. So hormonal imbalance, for example, or anything that impacts the transmission of nerve cells like scoliosis in the spine can impact the amount of stimulation and activation that the brain is getting back from the body. So there's a couple different facets, a couple different ways to look at stimulation. But nonetheless, let's dive into these a little bit further. So I apologize for the image here. This was copy pasted from lab results. I just wanted to show the clinical signs of anemia. So when you're diagnosing anemia, now let me put out a disclaimer really quick. As a nutrition therapist, legally speaking, I cannot diagnose, treat, cure, or prevent anything. However, I can point to labs like this and say, this is representative of low red blood cells. In this case specifically, it's low hemoglobin and hematocrit, which is the volume of the cells and the density. So in order for a doctor to diagnose anemia, either the red blood cells, the hemoglobin, or the hematocrit have to be flagged low on the lab. From there, basically what this is saying is we don't have, in this case specifically, either, in general, we either don't have enough red blood cells, we don't have enough hemoglobin. Hemoglobin is the transport portion of the red blood cells that actually the oxygen actually binds to transport through the blood. So in this case, we either don't have enough red blood cells or enough hemoglobin to effectively transport oxygen from the lungs to really any tissue for that matter. So from here, once this is identified, then it becomes a process of identifying what kind of anemia it is. There's dozens of different kinds of anemia. They are not all related to iron, to give you an idea. So whenever somebody says anemia, don't immediately think that you need to start taking iron. There's different types of anemia. It's up to whoever you're working with. You know, I'm capable of doing this, just not from a diagnosing point of view. Any doctor is capable of doing this. It's up to us to determine what kind of anemia it is and then provide the right approach to rebalancing it. Nonetheless, though, the point being, the take-home message of this is anemia causes a lack of oxygen, which can lead to reduced function of the neurons and really all tissue for that matter within the body. Next, we're looking at the nutrient side of things. So as I mentioned before, it needs neurons in order to survive. They need fuel and nutrients. Nutrients, as seen here, there are many nutrients, vitamins, minerals, phytonutrients that are needed in order to produce neurotransmitters. Now, remember, neurotransmitters are basically what allow us to do anything. It's how neurons communicate with each other. They'll send different neurotransmitters in order to relay a specific message. So if we are deficient in any of these nutrients, we won't be making the adequate amount of neurotransmitters. That relays to a breakdown in the system. Now we don't have enough of the raw material, we won't have enough of the neurotransmitter, and now whatever the nerve is trying to accomplish, it won't be able to accomplish at the fullest level that it was attempting to. So take serotonin, for example, the bottom left, the first one there. Serotonin is the feel-good neurotransmitter. It is a very calming, kind of a happy-go-lucky, take things in stride neurotransmitter. It also is associated with like satiety and appetite control. So, people that complain of having a hard time, like food cravings, for example, can be associated with serotonin issues or low serotonin. Serotonin is also the one that's most commonly implicated in depression, though it depends on which kind of depression. Norepinephrine and epinephrine can be, and dopamine for that matter, can all be associated with depression also. All right, with that said, look at the amount of nutrients that it takes and just different factors that it takes in order to produce serotonin. So B vitamins, B6, B12, folate, we've got vitamin C, vitamin D. Tryptophan is an amino acid. It's the precursor to serotonin. Magnesium. Then you look at normal thyroid function, intense exercise, gut function. This goes back to that concept of stimulation, right? Inwards and outward stimulation. But notice, almost all of these need B6. Almost all of these neurotransmitters need vitamin C. So if you have a deficiency in one vitamin or one nutrient, it's not just going to impact one neurotransmitter. It's going to impact many of them. And then in addition, this is just talking about the brain and the nervous system. Nutrient deficiencies, for example, magnesium is needed for over 300 different enzymatic reactions within the body. So if you're deficient in magnesium, which 75% of the population is, you've got 300 different enzyme processes that are going to be hindered, which manifests in many, many different ways from a body and function point of view. Okay, so nutrition, diet is huge, huge for brain health. When talking about ADD, for example, with children, nutrient deficiencies are hugely associated with that. B vitamins, for that matter, are major. So we cannot understate the importance of nutrition. The brain, in particular, is one of the most sensitive organs to nutrient status. Then in addition, from more of a macronutrient point of view, we've got blood sugar. So glucose, that's where the fuel component of neuronal survival comes in. The brain, even though it only weighs 2% of our body weight, the brain demands, it really gets preferential rights of 20% of our fuel intake. It prefers glucose. So glucose is sugar, blood sugar, glucose, those terms can be used interchangeably. We get blood sugar from the carbohydrates and protein that we eat from the diet. And then we can also, the body is capable of manufacturing its own glucose. So we can break down our tissue and different stores in order to raise glucose levels in the absence of food. So the brain prefers glucose. However, it is capable of running on fatty acids as well, specifically in the form of ketone bodies, not just fatty acids, specifically in the form of ketone bodies. We'll talk a little bit more about that when we talk about therapeutic diets, because ketogenic diets are extremely therapeutic for the brain and the nervous system. Ketones are a very clean burning fuel source. So we'll talk about that in a little bit. But nonetheless, if we're eating a normal, healthy diet, our brain is going to rely on glucose. Now, we need a steady supply of glucose throughout the day. Ideally, if you were to measure it, prick your finger throughout the day, ideally you're staying between 80 to 90. Really, you could even say like between 70 to 90. The lower end of the range, think of it like a car, right? You need your car to have a steady supply of gas throughout the day. If you're driving and your tank suddenly goes to empty, you're kind of screwed, right? You got to pull over on the road and then you got to call a friend and get gas or have it towed. It's this huge issue. Same concept applies to the brain and its need for blood sugar. So in an ideal world, understanding normal, we've got this steady supply of glucose, staying between the 70 to 90 range throughout the day. The brain has just enough to perform its optimal functions. However, what happens when blood sugar becomes dysregulated? as in either too high, consistently too high, hyperglycemia, or pre-diabetes, insulin resistance, and moving into diabetes. It could be too low, like hypoglycemia, or a mixture of the two, which is referred to as reactionary hypoglycemia, which is where your blood sugar is essentially doing this roller coaster dance throughout the day. So the numbers that I provide here, and I'm not going to go through each of them in depth just to be respectful of time, but you are welcome to pause the screen here. And if you have lab work, run and go grab it and then compare it to these ranges. These are used, these other markers, when evaluating lab work, you can't just base anything off of one lab marker. So these are all, I use functional ranges, which means they're determined by medical researchers studying healthy populations to determine what optimal is. And these are we're looking for blood sugar dysregulation. So hyperglycemia tends to be the most prevalent issue. That and reactionary reactionary hypoglycemia, the roller coaster dance, in other words. So hyperglycemia is where blood sugar is staying persistently high, measurable when it's consistently at least 3 times higher than 100 milligrams per deciliter in a fasting state, the blood sugar is. And over time, if you think about sugar in the blood like a Chinese throwing star, it kind of nicks and injures blood vessel walls and then also directly injures neurons. Hyperglycemia is associated with nerve cell death. This is why diabetics, for example, neuropathy is a very, very big concern. If left untreated, it can get to the point where it actually causes neuropathy so severe that limbs have to be amputated, right? So it's very well understood that high blood sugar causes nerve cell death. This is also part of the reason why Alzheimer's is referred to as type 3 diabetes. It's happening in the brain, specifically the hippocampus, as opposed to happening in the limbs. So high blood sugar is very dangerous for the brain, especially, or nervous system in general, especially when prolonged. Low blood sugar is also a stressor to the brain, or an imbalance of the two where blood sugar is spiking and then crashing and then spiking and then crashing, because, like I said, the brain is essentially starving whenever you're in a hypoglycemic state. Now, we have mechanisms in place to ideally reverse that, but it's signaling the stress response system, and that's not something that's ideally, supposed to be done on a routine basis. So, take-home message here, blood sugar dysregulation of any kind, whether it be consistently high, consistently low, or a mixture, kind of roller coaster effect of the two, is associated with neurodegeneration and poor neuronal functioning. Okay, that summarizes in short the neurons. Now we're going to get into anatomy and physiology of the nervous system, looking at the glia cells. So as I mentioned before, neuroglia, which are also referred to as glia cells, they're essentially the helper cells of the nervous system. They actually outnumber neurons 10 to 1. So that's why I said I know neurons get all of the attention, but they really only account for 1/10 of the brain's overall weight and volume, for that matter. Each neuron is surrounded by 6 to 60 glia cells, and these glia cells, so neurons are very delicate, right? It used to be, the understanding used to be that neurons, once they die, you're done. You cannot reproduce them. That concept is starting to be questioned now, especially with the use of stem cells. Exogenous stem cell therapy has been shown to be able to reproduce neurons. Nonetheless, though, they are a very sensitive cell in general, so they need to be preserved. And that is why we have glia cells. So these glia cells help protect, help feed, and help insulate the neurons. Because they're so highly specialized and they're essential to body functioning, and they rarely reproduce on their own, the neuroglia are vital to maintaining a functioning nervous system. So they're really involved in almost every aspect of neuronal processing. There are 3 different types of glia cells: astrocytes, oligodendrites, and microglia. And we'll briefly kind of get into these. Really, the importance of it is understanding that they all have different functions. So astrocytes, for example, are associated with, they're the only ones that have receptors for insulin. So astrocytes are big in maintaining that protective blood-brain barrier, making sure that glucose, that each neuron gets a sufficient amount of glucose. They also regulate like the pH balance and electrolyte balance within the neurons. Oligodendrites are associated with primarily insulating the neurons. So think of an electrical cord. You know, there's always rubber insulating an electrical cord. Same concept applies to the nervous system. With neurons, it's called a myelin sheath, or a Schwann cell in the peripheral neurons. But nonetheless, myelin sheath, and it's a fatty membrane, essentially, that insulates the neurons. And the oligodendrites make up that myelin sheath. So the oligodendrites really help insulate the neurons, which enhances transmission of signals. And then there's the microglia. And the microglia is where we're really going to pay a little bit more attention to today. The microglia are essentially the nervous system's immune cells. So they're scavenging and protective cells that are found within the nervous system. They are also, specifically the central nervous system, they are also, they mediate the inflammatory response within the brain. So that's why when we talk about neuroinflammation under the causes of breakdown, we'll really talk about the microglia. Now looking more at the gross anatomy of the brain, we'll go over the regions of the brain. The brain has been divided into various lobes, and that is determined based on the functioning. So, for example, and it's really helpful to understand the various lobes, because then based on, and really understanding the various lobes and the functions that they are responsible for, because then you can start to identify which region of the brain, which lobe is being affected based on symptoms. So for example, let's take the frontal lobe. The frontal lobe is really what makes us human. It's associated with problem solving, critical thinking, planning, planning in the future, concentrating. The personality, the seat of the personality is thought to be in the frontal lobe. Behavior, active, conscious thought processes. The frontal lobe is thought to be the seat of consciousness. That and the brainstem, but the brainstem is, I'm using two different forms of consciousness. Consciousness from the brainstem means that you're alive. Your vital functions are operating, like breathing and heart rate. Consciousness from the frontal lobe is self-awareness, right? Self-actualization, self-perception. So injury to the frontal lobe, in other words, they've shown, like accident victims, for example, where the frontal lobe is injured, they can come out of that accident almost being a completely different person, like a completely different personality. They might have to relearn how to think. They might have difficulty problem solving and concentrating. And then quite literally, like I said, their personality can change. So the frontal lobe is essential to many of our human traits. Then there's the hippocampus, or the temporal lobe. So the hippocampus is a region within the temporal lobe. The temporal lobe is the area right between, kind of where in between the ears, essentially, really in between the temples, hence the temporal lobe. It's associated with language, hearing, and auditory functions. But then also, because the hippocampus resides here, it's associated with memory. And also the circadian rhythm. So the day-night cycle that every cell in our body is programmed to is also regulated within the temporal lobe. So the hippocampus is where memory and learning takes place. So learning and memory formation. And when there's degeneration within the hippocampus, that's where, Alzheimer's, dementia, insomnia, even for that matter, can start to manifest. So there's various regions of the brain that account for everything from, control of voluntary muscles and coordinated movement to feeling external sensations, body awareness in space and time, vision, language comprehension, posture, balance, movement. All of the different areas of the brain have different functions. We're going to spend a lot of time looking at the hippocampus, but then other areas as well. Function of the brain and physiology. So essentially, the brain controls everything via two, or most things really, via two main mechanisms. Those are nerves and hormones. So nerves are comprised of nerve cells, which we've talked a lot about, nerve cells, neurons, and they communicate with the rest of the body via the transmission of electrochemical messages or neurotransmitters. Hormones are chemical messengers. So the endocrine system and hormones are chemical messengers. So if the nervous system is the equivalent to placing a phone call to a friend in order to relay a message, hormones are the equivalent of sending a letter to a friend. It's a little bit slower. It has to go through the blood system, the cardiovascular system. But nonetheless, those are the two main systems that are used in order for the brain to kind of keep tabs on the rest of the body and control it accordingly. There's two different divisions within the nervous system. These are all under the umbrella of the autonomic nervous system. So we've got the sympathetic and then parasympathetic. In short, because these are kind of big topics to undertake, but in short, the sympathetic nervous system is the fight or flight. It's the activated stress response side of the autonomic nervous system. And then the parasympathetic is its counterpart. It's the rest and digest. It's the calming side of the autonomic nervous system. Autonomic meaning automatic, in other words, so it's not under our direct control. We don't think about our heart breathing. We don't think about we don't think about our heart beating. We don't think about if the fact that we're breathing or not. These are just things that are automatically done under the control of the autonomic nervous system. Okay, let's get into the meat of the presentation and look at the causes of breakdown. And this, we're looking at the environment, diet, hormones, toxicity, and this comes out or manifests as neurodegeneration, mental illness, neurological disorders, whole nine yards. So signs and symptoms of brain decline. Some of these might be obvious, and then some of these might be kind of surprising. For example, like I mentioned at the beginning of the presentation, how many of us walk into a room and forget why? Or forget where we parked our car in the parking lot? How many times have you been holding onto your cell phone while looking for your cell phone? How about poor or worsening balance and coordination, worsening handwriting, difficulty recognizing objects and faces, difficulty focusing on tasks or easily distracted, leads us into more diagnosable conditions like ADD, ADHD, mood disorders like depression, anxiety, bipolar disorder, other signs of mental illness or conditions of mental illness like schizophrenia, for example, neurodegenerative disorders like Alzheimer's, early onset dementia, ataxia, which is an issue with motor coordination, autism, Parkinson's, diagnosable autoimmune conditions like Hashimoto's thyroiditis, experiencing a traumatic brain injury. That can lead, that can oftentimes be the trigger to a lot of these. So, in other words, the point of this is showing even our children are showing signs and symptoms of brain decline, right? And when you consider the fact, I mentioned at the beginning that it's our environment, when you consider the fact that there were 197 different chemicals identified within the umbilical cords, that gives you an idea as to why our children are being so greatly affected. So it's no longer the case that, it's just my memory, I'm getting old. That's not the case anymore. We see some teenagers that are really struggling with being able to concentrate and keep up in school. A lot of the people that I talk to, a lot of the clients I work with complain of brain fog. They just can't think clearly. It's difficult to process thought. So this is becoming ubiquitous, in other words, and it's impacting a large majority of our population of all ages, shapes, sizes, gender, ethnicity, everything. So let's look at the three main models that are associated with the breakdown of the brain and the nervous system. The first model that we'll look at is the excitatory model of neurodegeneration. Now, technically speaking, this class that I'm giving right now, I used to give in a 4-hour time frame. It was to students at the Nutrition Therapy Institute. It was a 4-hour class, and we really got into the mechanisms associated with this. But I want to make this understandable for the lay person as well. So I'm going to simplify a lot of this. The excitotoxicity model of neurodegeneration. If you recall the process of nerve transmission, where one neuron, essentially the electrochemical gradient is changed within a neuron, which sends an electrical chemical down the axon or down the chain of the neuron to the cell body. That stimulates the release of a neurotransmitter, which is the chemical part. The neurotransmitter then floats into space, what's called a synaptic cleft, binds to receptors or docking stations on the receiving neuron, which then continues and perpetuates the signal transmission down the line. All of this requires healthy mitochondria and adequate production of ATP. So let me translate that. Mitochondria they have many different roles, but mitochondria are associated as being the powerhouse of the cell. Any cell, every cell in the body, basically besides red blood cells, have mitochondria. So think of mitochondria as the factory of the cell where energy is produced. ATP is that energy. ATP, adenosine triphosphate, is the body's currency for energy. So when we're looking at the transmission of neurons and the production of chemicals, but especially just that electrical part of neurons, that requires a decent amount of energy. And if our mitochondria aren't functioning effectively, it's like having a factory that's gummed up, right? A factory that produces all of the city's electricity, but it is toxic and it's polluted and it's moving slow. That's probably going to result in the city having, some power outages, maybe even on the short term, some flickering lights in nearby businesses, but really power outages. Same concept applies here. So various environmental factors from anemia, poor diet, nutrient deficiencies, hormone imbalance, toxicity, an imbalance of the bacteria or the microbiome within the intestines. Many different things can cause our mitochondria to get gummed up, and they don't produce fuel as efficiently, which then translates to nerves not being able to send their electrochemical messages as efficiently, which manifests then as brain degeneration. Because what happens is now certain nerves aren't going to get that message. And when this happens consistently, like I said before, with the brain, if you don't use it, you lose it. So nerve cells will start to die. The nerve cells can also become too excited. They reach this hyper-excited state. And again, they essentially kind of short out and die. So this is one mechanism of neurodegeneration, is this excitatory model where the nerve cells are not able to keep up with the demand, or they're at a too high of a resting potential, and then any little bit of stimulation causes them to short out. And when nerve cells die, and especially when we get this kind of spreading effect where multiple nerve cells start to die, then that will manifest as, signs, symptoms, or diagnosable conditions. Next, we have the autophagy model of neurodegeneration. So I'm going to use the city as an analogy again. When you think about a city, there needs to be a balance between building new and repairing old. So with a city, we don't want to just build, but then never go in and, do maintenance on our buildings, do maintenance on our roads, repair the potholes, repair buildings so that they still function appropriately. At the same time, we want to be building new buildings because that will allow the city to grow and to thrive. And then if a building is breaking down or if a system is breaking down, sometimes you just got to tear it down, recycle the materials, and build new again. Okay, so take that analogy and apply it to the brain and the nervous system. Optimal neuronal function and metabolism requires both the synthesis and degradation or breakdown of proteins and balance. So proteins are what are used to essentially build anything within the body, but especially the nervous system. So neuron protein synthesis is necessary for cell growth, the support of neuronal transmission of signals, mitochondrial production of ATP, all of these things we talked about. So in other words, building proteins is necessary to maintain neuronal health and endurance and function. But there needs to be a balance. We need to build new proteins so that we can do everything that I just mentioned. And at the same time, we need to recognize when there are some old, degraded, kind of poorly functioning proteins and break those down, recycle, reuse their parts to build new ones. Autophagy is that cellular mechanism. Autophagy is the cellular mechanism for which proteins are degraded. So old ones are broken down, their parts are recycled, and we use them to build new again. Because as proteins are used, just like buildings, right? As they're used, they'll eventually use their structure and functional integrity, and they have to be degraded in order for proper neuronal health to continue. Poor clearance, so there are different factors that can hinder autophagy and hinder clearance. So poor clearance causes these proteins to aggregate, and it really, think of it like a river damming up. So if you think of the just normal nerve transmission as a flowing river, the aggregation of kind of degraded proteins dams up that river, quite literally damming up the transmission of the electrochemical message from nerve cell to nerve cell. Well, again, when that consistently happens and now the nerve cell isn't getting the stimulation that it needs, the receiving nerve cell isn't getting the stimulation that it needs, over time that will cause that nerve cell to die. And now we have neurodegeneration. This concept is specifically associated with Alzheimer's, but also Parkinson's, Huntington's, and more. But Alzheimer's, it's referred to as the tau protein tangles. So a specific type of protein called tau begins to tangle up and actually kind of dams up a certain area within the cell that blocks nerve transmission. And since this is happening in the hippocampus, when enough nerve cells start to die, it manifests as memory loss, right? And that's essentially what happens in Alzheimer's. Now it's memory loss, but then also there's other facets of the hippocampus. Like I said, the HPA axis, hypothalamus, pituitary, adrenal axis, the circadian rhythm that the hippocampus regulates, which is why Alzheimer's can eventually cause death. It's not just memory that's impacted, right? But nonetheless, it's poor clearance of proteins that this comes down to. So we really need a balance. One of the mechanisms or pathways, I should say, within the cell that's associated with autophagy is called mTOR. It's denoted by a little m as in mother, and then big T-O-R, T as in Tom, O-R, the mTOR pathway. And basically, when mTOR is not stimulated, it allows the cell to go into healing and repair, specifically stimulating autophagy processes. So clearing out old cellular debris so that the body can build new ones. So when it's not activated, it stimulates healing and repair and protein recycling. When it is activated, it stimulates protein building. It puts the cell into an anabolic state or a building state. We need both, right? Neither one is bad on its own. Neither one is bad. It's just when there's not a balance. Well, one of the aspects of nutrition that stimulates mTOR is protein, like protein that we eat, and glucose or insulin also. Both of these will stimulate mTOR. Now, don't get me wrong, I'm not saying don't eat protein, but I'm saying eat the right amounts for one. And then secondly, there's a way of eating that can also inhibit the activation of mTOR so that we do get into that more healing and repair zone. And that we look at restricting all food in the form of intermittent fasting. And then also this is where ketogenic diets can be really effective because fat doesn't stimulate mTOR in the same way. So more on that in just a minute, but I just wanted to reference mTOR in this while we're talking about autophagy. Okay, next we're going to look at the neuroinflammatory model of neurodegeneration. So inflammation gets a really bad rap, but it's not a bad thing. Very simply put, to define it, inflammation is the immune system's response to injury. Okay, that's it. It's the immune system's response to injury. We know that there's 3 categories of injury, and I'm going to use the terms injury and stress interchangeably here. So starting at the bottom, there's physical stress or physical injury. That includes traumatic brain injury or TBI, acute injury like you cut your hand or sprain your ankle, joint degeneration. Physical injury is anything that physically damages the tissues, in other words. You could also technically lump genetics into physical injury or infection into physical injury as well. Then there's chemical stress or chemical injury. This includes environmental toxicity, the food we drink, the food we eat, the air we breathe, the water we drink, hormone imbalance, food sensitivities for that matter, blood sugar dysregulation. These would all be examples of chemical stress. And then there's emotional stress or emotional injury. We all have this. Emotional stress counts as the day in, day out stressors like deadlines and work and traffic. It also includes the life-altering stressors like the unexpected death of a loved one, being a caregiver, any kind of emotional trauma for that matter. Well, if you look at the inflammatory cascade, which is what this is, if you look at the inflammatory cascade like a bucket, if you keep dumping water into a bucket, eventually it overflows. Same concept applies with inflammation, right? If you keep layering injury upon injury upon injury upon injury, eventually a threshold is passed, and this threshold is different for everyone, but eventually a threshold is passed where then symptoms and diagnosable conditions manifest. Genetics, just side note, genetics determine how and where those symptoms and conditions manifest. Genetics determine whether someone's going to get diabetes or cancer, right? They don't necessarily determine that it happened, they determine how it happens or how it manifests. So to reduce inflammation, we don't want to stop the inflammatory cascade. We have prednisone to do that. That is not a long-term sustainable solution. The name of the game comes down to identifying what the sources of injury are for each individual person, then prioritizing and systematically eliminating them so that the body can go back to healing itself. Okay, so that's understanding inflammation in a nutshell. Let's look at what happens with inflammation in the brain. So the brain and central nervous system immune systems are different and separate from the rest of the bodies. So they're all kind of encased within the brain, the skull, and the spinal cord. And then there is the peripheral nervous system as well, and the peripheral immune system. The immune system within the nervous system is comprised of glia cells, predominantly microglia. So if you remember that word from earlier, microglia cells are basically the immune system for the brain and the nervous system. They function similarly to macrophages. Macrophages are like this scavenging cell. They're kind of the first line of defense. They just troll around the body looking for invaders, looking for cellular debris, anything that's not supposed to be there. And then what they do is they engulf whatever they find, and they'll either digest it, in a vat of acid. Essentially, they'll digest it. And while they're doing this, they'll also release chemicals called cytokines and chemokines to signal other immune cells to the site of injury or the site of invasion so that they get help in fighting it off. So that is how microglia cells function. And that is their role. So when this happens in the nervous system, first of all, let's think about, kind of what microglia cells respond to. They respond to chemicals, environmental chemicals. They respond to any kind of food sensitivities where your immune system's going after food. They respond to different allergens. They respond to damaged cells or dying cells, those neuronal tangles or protein tangles I was talking about, toxicity. So they respond to many different things. And then, as I mentioned, they're scavenging for this. Let's say they find something, they engulf it, and then they release these chemicals to signal other branches of the immune system. Well, that's great, and that's how it's supposed to function. The problem is when this is happening on a consistent and high volume basis, those other chemicals, those cytokines, can be inflammatory in and of themselves. So those cytokines can damage innocent surrounding tissue, which then attracts more microglia cells, which then causes the release of more cytokines, and it becomes this vicious cycle. These cytokines are capable of resulting in what we call a spreading depression, where they kill neurons, and then those neurons can't stimulate the other neurons, which then results in those neurons dying, which then attracts the microglia cells, which perpetuates the inflammatory response. So, it's sad but true that brain inflammation, the activation of microglia, they really don't have an off switch. So once the microglia have entered this excitatory state and they're signaling the inflammatory response, they don't really have an off switch, and that can result in the death of the surrounding neurons. And then when neurons start to die, it really just depends on which part of the brain or which part of the nervous system the bulk of the neurons are dying. That will determine how symptomatically and diagnosably it manifests. So does it manifest as Alzheimer's? Does it manifest as Parkinson's? Does it manifest as autism? It just depends on where and how it's being affected. But the neuroinflammatory model of neurodegeneration is gaining a lot more attention because the nervous system and the brain is so sensitive to different environmental insults. So our brains are constantly under attack, in other words, and it's up to us to really do our due diligence in supporting it, reducing our exposure to, infiltrates, so that the immune system in the brain isn't constantly being activated and the brain isn't basically always on fire. So thankfully, even though the microglia cells don't have their own off switch, there are nutrients that can be found in food and various nutritional supplements that can serve as an off switch. So for example, some of the most well-researched, resveratrol and curcumin, are both, they help kind of mediate that inflammatory response. So they'll help calm the signaling and release of cytokines so that the cytokines themselves don't start to cause injury. So they serve as an off switch in that way. Vitamin D, glutathione, and omega-3 fatty acids, EPA and DHA, all of these support the immune system itself. So it can help calm down the immune response. It can help various branches of the immune system say, oh, okay, never mind. That battle's been fought. We don't need to continue the fight, in other words. And then once the invader has been addressed and eliminated, then the immune system can calm back down as opposed to continuing the battle, even, like I said, when there's not a battle to be fought. So nutrients can play a huge role in supporting the brain and rehabilitating the brain, which is where we're going to go next. Nutrition therapy to restore balance There's many different things that can be used, but I'm going to talk about some of the bigger ones. Therapeutic diet. So food will always be the foundation of health. If you're not eating a nutrient dense, low glycemic, anti-inflammatory diet, just quality whole foods diet, you're going to hinder your health by about 80%. So there are specific therapeutic diets for brain health, really. Ketogenic diet, the paleo diet, and intermittent fasting we'll talk about. There are specific nutrients, some of which we just touched on, then exercise and stress management. Okay, regardless of whatever kind of, quote, diet you do, I really don't like the term diet either. It really is more of a long-term lifestyle change. But regardless of what kind of, quote, diet you do, eating a plethora of fruits and vegetables and nuts and seeds and brightly colored foods ensures that you're getting a diverse supply of micronutrients like phytonutrients. So each of these the colors are significant because it means nutrient density, in other words. So eating a variety of whole foods, organic, definitely organic, like I said, fruit, vegetables, healthy animal products, grass-fed, grass-finished, animal products, free-range, wild-caught, all of those disclaimers. Healthy fats like avocados, nuts and seeds, coconut, even grass-fed butter, and then moderate amounts of protein. All of these are essential. It's kind of the foundation of any nutrition plan. And then we can take it and personalize it from there based on the strategy that we're trying to take and what we're trying to achieve. So the ketogenic diet, for example, ketogenic diet is getting a lot of notoriety within even the conventional medicine world for its effectiveness in various neurological disorders, specifically epilepsy. That's gotten a lot of attention in the research, but then also autism and Alzheimer's and Parkinson's. So the ketogenic diet is founded on the premises of ketosis, the state of ketosis. So I have a presentation also on ketosis, so stay tuned for that, ketosis and the ketogenic diet, so stay tuned for that. But in short, ketosis is a natural state for the body to be in. It's the body's response to either starvation or very, very, very low glucose supply, low sugar. And in that state, the body will essentially shift into a fat-burning state as opposed to a glucose or a sugar-burning state. So your body will start to either break down your own fat or utilize the fat from the diet, which is why ketogenic diet, the hallmark is a diet very high in fat. It will break down fat and combine and produce ketone bodies. Ketone bodies there's 3 different types of ketone bodies, but there are different forms of acids that can be used for fuel, a very high density, clean burning fuel supply. So going back to the mitochondria and the concept, relating mitochondria to factories and cities, how it's imperative for mitochondria to be clean so that they can create and manufacture fuel efficiently. Ketones are a very, like I said, high density, clean burning. So they're great for mitochondrial health. The various acids, acidity associated with these different ketone bodies too, can impact the pH and cell signaling associated with neurons, which is part of the reason why, part of where it's being proposed to be effective for epilepsy. So there's many different therapeutic applications. And then not to mention, just very simply put, the brain is 60% fat and cholesterol. So the brain is comprised of fat. So it makes sense as to why a ketogenic diet would be therapeutic and effective for neurological disorders. So to recap, ketones are derived from fatty acids, shifts the body into a fat burning versus glucose burning state. They are a high density, clean burning energy source. Ketone bodies also enhance the process of autophagy. So they help break down those old proteins so that the mitochondria can build new proteins. They generate less oxidative stress, so they're cleaner burning fuel supply, as I mentioned before. And then they also, they're great for the mitochondria because they don't produce as many toxic byproducts. And then the brain is 60% fat, so a diet high in fat will naturally support brain function and growth. And then lastly, the acids associated, the three different kinds of acids, beta hydroxybutyrate, acetoacetate, these different kinds of acids that are so different kinds of ketones can have a positive effect on the neurotransmission of nerve cells, which is partially where it's thought to be helpful with epilepsy. In a ketogenic diet, it's very tightly controlled. So roughly 70 to 85% of the diet comes from healthy fat. So what that looks like is you're eating a lot of fat, right? You're either eating, a bunch of avocados, you're adding more oil to a meal than you normally would, while at the same time significantly reducing your carb and protein intake. So specifically carbohydrates, basically, non-starchy vegetables like leafy greens, some peppers, artichoke, cucumber, celery, things along those lines. Some nuts and seeds are really going to be the main source of carbohydrates. So no sweet potatoes, no starchy vegetables, no fruit. Now, once you get into ketosis and you're able to maintain it for a period of time, some people's tolerance for carbohydrates will get a little bit more lenient. So I encourage people to be strict up front, get into ketosis, which is you can measure in blood ideally, but also urine, and then start to play around with it and see what you can get away with from a carbohydrate point of view. And then there's protein. The thing with protein is it can be converted into glucose. So in the presence of insufficient amounts of glucose, your body will convert protein into glucose. So protein also needs to be limited. So we're looking at very, very modest amounts of animal protein. I mean, maybe 1 serving up to 2 servings per day, small portions like 3 to 5 ounces of animal protein. And again, just play around with the numbers and how much you can eat while testing your ketone levels to ensure that you're staying in it. But a general rule of thumb is about 1 gram of protein for each kilogram of body weight. So convert your body weight into kilograms by dividing your weight in pounds by 2.2, and then multiply that to get your weight in kilograms, and then multiply. That's the amount that you'll need of protein per day in grams. All right, so that's a ketogenic diet. Very, very, very high fat, low carb, modest amounts of protein. And that will put your body into a state of ketosis. This is just simply a study that looked at the effectiveness of a ketogenic diet on various neurological conditions, specifically Alzheimer's and epilepsy. Again, if you want to read through this entire, the entire passage here, feel free to pause the presentation. Intermittent fasting. Intermittent fasting has been getting a lot more, also like a ketogenic diet, a lot more notoriety lately, even within the conventional medicine world. So intermittent fasting, basically what this looks at is it started by studying the benefits of caloric restriction. And in caloric restriction, I mean, the benefits have been, everything from weight loss to longevity. But typically studies were looking at 20 to 40% reduction in daily caloric intake, which frankly is hard to maintain. So intermittent fasting arose as a means to reproduce the benefits of caloric restriction in a reproducible way. What intermittent fasting involves is eating within let me also say, the term fasting in the research is determined by at least 12 hours of no food. So once you reach that 12-hour mark, that is when you're considered to be in a fasting state. So intermittent fasting involves reducing, fasting for a minimum of 12 hours, but ideally up to 16. That's kind of where the magic happens. Fasting for 16 hours, typically while you sleep overnight, and then eating later in the day, like late morning or lunchtime. And then you eat a full day's worth of calories. So you eat all of the food that you normally would within an 8-hour period. So let's say you finish eating dinner at 7 o'clock at night. The next day, you would fast until 11 o'clock the following day, 11 o'clock in the morning the following day. And then between 11 a.m. and 7 p.m. that day, you would have breakfast, lunch, dinner, snacks, everything, normal beverages. You would eat normally and then repeat the cycle again, fasting for 16 hours. This has profound benefits. So not only does it, everything that we just talked about, right? It really addresses everything that we just talked about. It lowers insulin levels. It lowers leptin. Leptin is a hormone produced by fat cells that relays satiety, feelings of satiety to the brain, signaling basically that we've gotten enough fuel. IGF levels, IGF-1 has been associated with cancer, for example. It promotes ketosis. So fasting, this form of intermittent fasting doesn't mean that you'll get into ketosis, but if you're following a ketogenic diet, then intermittent fasting is a great way to enhance ketosis. So it promotes ketosis, reduces reactive oxygen species, which is what ROS stands for. Reactive oxygen species are oxidative stress. So it's the process of our cells essentially rusting, right? Rust is the same concept or the same process. If you leave an apple out, cut an apple in half and leave it on the counter and it turns brown, that is the result of oxygen, reactive oxygen species. Same thing happens within our bodies, and these ROS molecules damage our cell membranes, they damage our mitochondria. So this is also where antioxidants are helpful, because antioxidants neutralize reactive oxygen species. So it's a good thing to reduce them. We'll always need a little bit of reactive oxygen species. It's a good kind of stress, but we don't want excess amounts. It promotes autophagy, that healing and repair, breaking down those old proteins that we talked about before so that your body can build and recycle new ones. And then it inhibits that mTOR pathway I was mentioning before, that important metabolic pathway responsible for either tissue healing and repair or growth, depending if it's stimulated or inhibited. And intermittent fasting inhibits mTOR, which puts that mTOR pathway into the state of healing and repair. So it's a very easy thing to incorporate into our daily lives, right? You just change the timing by which you eat food. You don't even have to reduce the amount that you're eating. You just change the timing. So you can do this 2, 3, 4, 5, 6, 7 days a week, whatever fits into your schedule. And then there are specific nutrients for supporting the blood-brain barrier and neuroinflammation. A lot of these can be found, they're kind of anti-inflammatories and antioxidants in their own right. A lot of these can be found in blends. So there's different supplements that have blends of these. But you can find they're also found in whole foods, right? So that's another reason why always you want to eat a diet rich in variety of whole foods. So again, anti-inflammatory, they help neutralize the activation of the microglia cells, reducing the inflammatory response within the brain. They can also support brain cells themselves, the neurons themselves, or the immune system, like EPA and DHA. The essential fatty acids are used to support the myelin, so that insulating factor around neurons. And then glutathione, vitamin D, calming down the immune system, really balancing out the immune system. So there's many different nutrients that can be supportive of brain function and really start to calm down the inflammatory response, support mitochondria, many different aspects to health. This is a study citing the effectiveness of curcumin and neuroinflammation. Again, if you want to read this, you can pause the presentation and actually read the abstract of the study. Continuing on. And then same thing, looking at antioxidants, phytonutrients, and brain degeneration, the neuroprotective action of natural compounds. And then we look at exercise in the brain, which is where we're going to wrap up. Exercise it's just incredible for the brain. It has the ability to cause the distinct release of brain-derived neurotropic factor. So basically, BDNF for short. So basically, exercise is like Miracle-Gro for the brain. Brain-derived neurotropic factor is this protein that allows neurons to undergo what we call arbitration. So form new connections. If you really, going back to the dendrites of neurons, the dendrites were those kind of, they looked like trees, right? They just looked like trees where they're branching out. Those limbs, if you will, then make connections to other neurons. And it's that connection, it's those new connections is how we form new skills. It's how we learn new information. So arbitration is the process of keeping the brain young, healthy, and active. Brain-derived neurotropic factor is the protein that promotes that process. So it allows the neurons to form dendritic branches to each other. And this is critical for the survival and the efficient functioning of neurons and neuronal transmission, respectively. And exercise is one of the best ways to do this, to literally keep your brain young, active, and healthy. There's been several different studies. This one is quoted from Harvard Health back in 2013, that exercise is just as effective, if not more than, antidepressant medications for mild to moderate depression. So exercise, really any kind of movement that you enjoy doing. If you like going to the gym, great. If you like dancing, fantastic. If you like running, skiing, swimming, it doesn't have to be the traditional exercise, nor do you need to allow an hour a day for it. They're high intensity interval training, or HIIT for short, HIIT. There's YouTube videos all over the place that have HIIT training, exercise programs that you can follow. But HIIT involves 10 minutes, high intensity interval training. So 10 minutes of intervals between high intensity, like all you've got exertion, alternating with periods of rest. So like 30 seconds on, 30 seconds off, for example. And that once per day has been shown to mimic the benefits, if not actually elicit some more that are not associated with the endurance style, 30 to 60 minutes of training. So you don't need much time, in other words, to get exercise. Go for a walk, go dancing, do yoga. Any of those are effective. Your brain will thank you. All right, guys, that concludes the Why Isn't My Brain Working Part 1 presentation. Again, in Part 2, that's where we're going to explore the underlying causes of these sources of dysfunction. So what causes poor autophagy? What causes the excitatory model of degeneration? What causes neuroinflammation? Things that we're exposed to in our everyday environment, right? So that's where we'll explore that component. I really hope this presentation was helpful for you and allows you to do some reflection on what might be causing some of your own health concerns. As always, if you would like more guidance in identifying and addressing these issues, please do not hesitate to reach out. I offer complimentary 15-minute consultations, the Gateway Health Package. There's many different options so that we can get you on the path to realizing and achieving your optimal health. Okay, thank you everyone so much for your time. Enjoy the rest of your day. Goodbye.